Hi everybody, welcome to my YouTube channel. In this video, I want to talk about how HY8 does the normal depth calculations. Now let's take a look at HY8 and its tailwater channel. I'm going to add a new crossing here, and then I'm going to give it 10 CFS peak flow. And I'm going to define a rectangular channel as tailwater data and give 10 foot of bottom width and 0.001 feet over feet as channel slope. Let's say it's a concrete channel. I'm going to make it like 0.13. And then I'm going to take a look at the rating curve. HY8 reports the flows from 1 to 10 CFS because we have defined our maximum flow as 10 CFS, and for each corresponding flow it calculates the depth and velocity and shear stress. I got curious and I just wanted to compute those values to make sure that I understand what HY8 is doing for tailwater channel, and I believe that it's doing normal depth calculations for that. So for a rectangular channel, let's take a look at how it's done. So here is the code I have developed to do that. So I use Python programming language and I'm coding in Notepad++. They're easy to download, they're free applications. And then I used Kinter for my graphical user interface. So I have imported Kinter and message box first. And then I have imported some matplot libraries so that I can plot my cross section, and I also use math library in my calculations. So I have created a global axis and canvas so that I can show everything. This function is for Manning's equation. I have calculated my cross section area, so bottom width and 2 times side slopes times depth. That's my top width. And then if I get top width and bottom width, if I add them together and get the average and multiply it with depth, it's my flow area. This is my width perimeter. It's basically bottom width and depth times side lengths. And then this is my hydraulic radius, and if it's 0, if the perimeter is not defined, it's gonna be 0. And this is the velocity equation for Manning's. And I will return peak flow, area, perimeter, hydraulic radius, and velocity. So this is my bisection normal depth function. So let's talk about bisection method first. To be able to do that, I have like a target peak flow, and I'm trying to reach that peak flow in this function. B is my bottom width for the cross section, Z1 and Z2 are my side slopes, and for roughness, S for channel slope, and I defined a tolerance. So if the tolerance is less than 4 decimals, it means that I have reached the desired peak flow I'm trying to reach, and I want to limit my iterations up to 500 iterations. If I have more than 500 iterations, I want to quit. I want to get out of the loop. I don't want to create an infinite loop for this. So in this line, I declare that my minimum depth and maximum depth is going to be like 0.001 and 100 feet. If it's not within this range, I can't get there, but I don't think it's going to be a problem for this calculation. So I define my f function. F function is the Manning's equation, and then I just define the Q target, and I'm trying to make this function 0 in the bisection method. If you're not familiar with the bisection method, you can search online. There's a lot of resources on the net, and there are a lot of YouTube videos about what it is mathematically. So here is the spot that we need to talk about. So if my function times like y low and y high, if I multiply them, if I bigger than 0, it means that there is no real solution in this range, y low and y high range. So I have to update, I have to change these elevations for them. So I start iterating to up to like maximum 500 times, and then every time I calculate, I get the midpoint. Midpoint is like the average of low point and high point. So I get the f function for the midpoint. So I do this if statements to check that my midpoint function is less than tolerance. It means that there's a solution, and I return this mid depth. If not, it means that I need to continue for my calculations, and then I get the y high as the midpoint, y low as the, or y low is the midpoint, depending on what the result is. And I keep continuing, and after 500 iterations, if I can't reach anywhere, if I can't find any real solution, I print some statement in the function. I say bisection did not converge. So it means that you either have to change the low and high values or adopt another approach, do something different. Then I define another function. It's called safe float conversion. So if I give a value in my graphical user interface, if I cannot convert it into a float, I'll return none. So I want to get float numbers. I don't want to get any text or alphanumerical value into the calculations, so that it's gonna crash. So here is my update result variable function. So if I can reach the solution, that's what I print. I print everything I have reached. So normal depth, cross section area, weighted perimeter, hydraulic radius, velocity, and shear stress. I print everything in 3 decimal precision, and I write them line by line basically. So my calculations start here. So I get like QB, Z1, Z2, N, S, everything. I convert them into float, and I get all the variables as from entries. I'll explain what entries is soon. So I take Q, peak flow, like B, bottom width, Z1, Z2, side slopes, roughness or channel slope. If I cannot convert them into real numbers, floats, I raise an error and I say please enter valid numeric values. And I assume that none of them will be less than 0 and equals to 0. So if Q or any of them are 0, it means that there is no flow basically. And if they are negative, mathematically I'll come some irrelevant output. It's not realistic. And what I do is I try to calculate depth with my bisection method that I have created here and get the results. If I can't reach to any real solution, I say fail to compute normal depth and return it. If I can reach it, I get the calculated peak flow, area, perimeter, hydraulic radius, velocity, everything. I also calculate the shear stress with this equation. It's 2 times gravity times depth times channel slope. And then I update my results with this function I have created here, and then plot everything. So let's talk about plotting. So what I do is, here is my axis and canvas I created globally on top here, and then here is my left bottom corner. I put it to 0, 0, and then right bottom corner, which means bottom width and 0, and I calculated top left and top right points so that I can plot my cross section. And here is my plot. I just draw all the lines for the trapezoidal cross section. Basically I'm doing it for trapezoidal cross section because rectangular cross section is a specific case for that. In this case, if I can do it for any like trapezoidal cross section, I can use it for rectangular cross section if I put Z1 and Z2 as 0 into the program. And then I plot the ground elevation and I plot the water surface elevation. It's basically just, you know, Python coding, just plotting. It's not about the calculations. And then when I print and plot everything, it's fine. So then I put this into a try and except, you know, statement, so that if there's any crash, anything, you can just, you know, print could not load watermark or anything like that for my logo. And then I also put the text, and I want to add some, you know, scale information and stuff like that, and that's it. So here is my graphical user interface. I created a root in Python Kinter, and I said root title will be, you know, Beyond Water Resources Prismatic Channel Flow Depth Solver. I put my icon here, and I put some labels. I want to show which button or which, you know, entry is what, so that the user can understand what it is. I put all of them, and then what I do is I get all of them, you know, into a kind of like good canvas, and I could locate them on my user interface. And then I put a button, so when I click on the button, it's gonna do the calculations. It's written calculate in the button, and when it's clicked, it triggers calculate function, which is created right here. And then after that, this is the results. It gets the results, and then kind of I put them on the user interface, and then after that it plots, and then this is the main loop of the function. Oops, sorry, I have to go back and keep it like that. So that's what I did for this. Let's see if it's gonna work or not. So this is the file that I have created. I have saved this as Manning's Prismatic Channel Solver, and I saved it as a pyw file, which means like a window or something like that. When I click on it, I don't want to open the black, you know, window in Python. That's what I did. And let's click on it, and then let's see if it's gonna work. So here is our solver, and let's put 10 CFS peak flow and 10 foot of bottom width, and 2:1. Let's do, yeah, 2:1 side slopes, and then let's put Manning's roughness as 0.013 and 0.001 side slope, and let's click on the button. So it's calculated. This is my normal depth, this is my flow area, weathered perimeter, hydraulic radius, velocity, and shear stress. I have also plotted my cross section like that. So the blue line is my water surface elevation, and the brown one is the ground elevation. So I put my scale here too. When I change these and calculate, every time I calculate, it's gonna change my plot too. So let's go back to HY8. Okay, this is our HY8 calculation, and in this one we did some rectangular calculation. So let's go put 0 for side slopes and say calculate. So here is the rectangular channel cross section calculation for a tailwater channel. So if we look at here, if we say view, and if we look at this one, you can see that the depth, flow depth, matches the HY8. So we know what HY8 is doing now. And then velocity is 2.084, and this is our velocity, and the shear stress is 0.03. So that's what we have is, you know, PSF. So that's good. If we make like 2:1 side slopes, it's gonna be a trapezoidal cross section, and then we can check that too. We can make this trapezoidal cross section. We can put 2:1 side slopes, and then if we say calculate, let's see if it's matching. See, normal depth is 0.457, which is the same, and velocity 2.007. So now we have everything HY8 does for normal depth calculations in a prismatic channel. There are other types of cross sections. I will try to handle them in the next videos, but for today, that's what we have. And we have a better, you know, representation of the cross section too, because we can see it as shape too. For trapezoidal and rectangular, I don't think that HY8 can plot that. And that's all for today. I think we have figured out how HY8 takes care of the tailwater channel. Thank you for watching my channel.